applications. Magnetism, types and properties. Hard and soft magnetic materials, applications. Dielectric types of polarization. So these are the contents of your unit 3. Do you see the unit, the syllabus slide 2, slide number 2? Hello?
Yes, sir.
Okay. So we'll continue on. Although the syllabus straight away jumps to Drude theory of electrical conductivity, but the topic of the unit is solid state physics. So perhaps you have to have a clear-cut understanding what solid state physics is about, or the definition of solid state physics itself. So we all know that materials or matter exist in three forms: solid, liquid, and gas. One best example that our day-to-day life we consume or use a lot is water. Okay, so water in normal atmospheric condition, that is our Earth's atmospheric condition, the pressure, volume, temperature, entropy. These are the four thermodynamic conditions. In our Earth's thermodynamic condition, water is H2O. The molecule H2O exists in the form of liquid. But you know that we can put some quantity of water and put in your refrigerator and keep it for some time. If you put in the freezer, you get ice. So of course we consume ice too, eating ice or drinking ice, having ice cream like that. So we can make water into solid. And also when we cook, we use water or make a cup of coffee or something. You boil the water, you heat the water and it boils. While boiling, some water molecules actually getting evaporated and becomes gas. That's called steam. Okay. So it's one best example. So solid state physics is dealing about the solids. Okay. So what you have to understand and accept is that any material that you have in your life, or you can see them, would be transformed into gas or liquid or solid, irrespective of the state of matter that exists. Okay, so water exists in the form of liquid in our Earth atmospheric condition, means thermodynamic condition. But if you perhaps take another material, maybe iron. Iron we use a lot, right? We make steel and other stuffs. So iron is not in the form of liquid, not in the form of gas. In the thermodynamic condition of the Earth, we have iron in the form of solid. Okay. There are steel bars, iron bars, so many things we use for building purpose and so many things. Okay, so depending on the chemical content, okay, of a matter, okay, in the same atmospheric conditions, the same thermodynamic conditions, same pressure, same volume, same pressure and same temperature, and maybe same entropy in the Earth's atmosphere, we have iron in the form of solid, whereas we have water, H2O, in the form of liquid. Okay. It's interesting thing. Okay. So a lot of things which we use in modern days are solids, especially when we come to technology. We use a lot of solids. Of course, we do use liquids and gas as well, but a lot of devices that we use are solid state devices. You take laptop, mobile phone, is there main component or major components in liquid form or gas form? No, it's all in the form of solids. So that's why we have a separate branch in physics called solid state physics, which has a lot of information, a lot of developments and understanding that comes out of solid state physics, and it has also produced a lot of applications that are flourishing our life, day-to-day life, and transform our life quite a lot. Your syllabus contains so many different things like materials like semiconducting materials and application. You know, there is a superconducting materials. Those are very important, interesting things. So we will learn as best as possible. So as the subject is vast content, even solid state physics, a master degree PG student of physics, MSc physics students learn solid state physics in two course, solid state physics 1 and solid state physics 2. Okay, such a vast subject. Still, that's not complete. There's quite a lot of things to learn, but it is a part of one unit in your course. So we can touch up the surface level and give the important information to you, and you can proceed further. Okay. So what you see in this slide is actually These structures are the structures of ice. Okay, basically snow. If you go to the region where you get snowfall, the northern states, in Jammu Kashmir, or other countries like United States and all, or Canada, you get snowfall during the December to roughly February month, December, February, you get snowfall. If you carefully notice, you can see these beautiful structures. The snowfall is nothing but the water molecules that is frozen, and they have very beautiful structure with it, pattern. Okay, these structures are very beautiful. They have quite a lot of symmetric appearance. Okay, very beautiful structures. You can see them. So there are 7 structures are shown here, and what is shown on the right hand side is a huge pillar. We can say pillar. Okay, pillar of silicon dioxide. Quartz crystal, silicon dioxide molecule arranged in a particular pattern, the special arrangement that give rise to a crystal structure called quartz crystal. And that quartz crystal, you can see it's several folds or several times the height of an average human being. You can see the width and the height is terribly huge. These quartz crystals are not simply something junk, they are very useful. Quartz crystals are used in digital watches and digital wherever you want digital timekeeping. You need quartz crystal. You can use quartz crystal. You can cut the quartz crystals in a particular specific direction and thin down in specific thickness, etc. And then if you apply some potential to them, they can be used to maintain time. Okay, so all digital watches have a small cylinder shape component that actually would appear like a capacitor. Okay, but it's not capacitor actually. If you open and see inside, there will be thin plate of quartz crystal. Okay, that quartz crystal is actually powered with the battery, and that quartz crystal vibrates with respect to time because of the piezoelectric effect, and that vibration is actually maintains to keep time. So for a given potential, how many times it vibrates, or that frequency of vibration. You remember we learned the oscillation vibrations or oscillations in the unit 1. So that has a time period. So using that calculation, you can maintain timing, and you can use for the other electronic circuits and components, or LCD display units, etc. And then we build a digital watch. Of course, in the modern days we use smartwatches. They also use digital watch. It's digital display with a lot of other capabilities to maintain, to measure and display your blood pressure, etc. So anyway, there is quartz crystal. So they are very useful. So these are some applications. One important application, set of important application of solid state physics. Do you see slide number 4? Slide number 4.
Yes, sir.
Okay, so this is what I mean. Once again, it appears water appearing here, that we have in liquid form basically water. You can use it for cooking purpose, or you can freeze it and make ice and make a juice. Okay, and drink cool for the summer. It's very good. This is a snowman toy people use in the Western world. And this is steam. When you heat, maybe when you make a cup of coffee or tea, you get steam produced. And the snowflake structure, which we have discussed detailing in the future, in the previous slide. What you see, the next one is solids are classified based on the arrangements of atoms. Okay, so solids are. So we saw that matter is classified based on certain parameters like its density and the average distance between two molecules or atoms in the system. We classify them solid, liquid, and gas. In solids, the average distance between any two molecules or atoms are smaller, very small. But when you go for liquid, it is slightly larger. When you go for gas, it is still larger. Okay, likewise we saw, and we also know that solid assumes its solid has its own specific shape and volume, whereas liquid assumes its the shape of the container and volume is fixed for itself. But for volume, by giving a pressure and also it can assume the shape, but it's not having basically any shape, but it can be thought of assuming it's shape of a container when you have a closed vessel like that. So there are some certain properties like this. So based on that, we classify matter into solid, liquid, and gas. Now the solids itself are classified into few forms, such as amorphous solids, polycrystalline solids, and single crystal solids. Okay. You see what is the key difference? There's a nice arrangement. Okay, each black circle represents an atom. If you assume each black circle representing an atom, when you look these three form of solids, amorphous solid, polycrystalline solid, and crystalline solid, which one seems more symmetric or more regular arrangement, more clear, perfect arrangement? Single crystals, right? You see the given piece, the entire volume, that's a clear one single regular arrangement of atoms. So it is called single crystal. Polycrystalline material contains actually two or more crystals. You can see two units of crystal, left side one and right side one. In between them are connected by something. Okay, so you see two or more crystals, only two is shown here in this picture. So there is a clear and perfect arrangement, but there are two types. One is on the left side and the other is at the right side, and both are connected. So it is called polycrystalline. Poly means more than one. So polycrystalline. Whereas look at amorphous solids, there are atoms, they are bonded together, but there is no regularity, there is no any arrangements of clarity. Okay, they are just randomly distributed. So that set of type of solids are called amorphous solids. Okay, in application point of view, all type of solids are very important. All type of solids are useful, but depends on the material. For example, if you take silicon single crystal is very much useful for making all type of electronic devices, transistors, or any type of computer chips you can imagine is based on silicon single crystal. You need very, very perfect arrangement of silicon atoms in the material, and that also needs to be very, very pure, no impurities. So then we can control. We learn further details about semiconductor studies with semiconductors. So that is useful for making devices. Polycrystalline material. Polycrystalline materials, quite a lot of them they are used. For example, there are materials that are called ferroelectric materials. It's part of your syllabus. They are useful for storing data, and also materials such as piezoelectric materials. They are useful for gas igniters, etc. Okay, they produce spark when you hit the crystal. When you compress or heat the crystal, they produce electric pulse. Okay, there's a huge electric potential that is maintained between two terminals, and that will be discharged to the atmospheric air, and that produces a spark in the atmosphere. That spark, in the surrounding there is any combustible gas molecules available like LPG, etc., it will get ignited. Petrol, it get ignited. So polycrystalline materials also are finding very useful applications. And amorphous material, silicon, once again, amorphous silicon and polycrystalline silicon, single crystalline silicon. These are different types of silicon materials. They are useful for solar cells, converting light energy, sunlight into electrical energy. There are a variety of different types of solar cells. They are also a part of electronic devices. They are useful. The different types of solar cells are available, amorphous and polycrystalline silicon solar cells. Okay. So what you see in the bottom most on the right side of in this slide is stone. Like there is a stone. On top of the stone, there are some very perfect cube-shaped stuff. So these are nothing but iron disulfide crystal called pyrites. Iron disulfide crystal called pyrites. This is how a single crystal typically look like. Of course, depending on the chemical composition, iron disulfide will look differently. Quartz will look differently. Quartz looks typically white, sometimes very transparent, which is very pure. And if there is a small impurity with that, according to the chemical composition of the chemical of impurity, it will have a different colors. Okay, or for example, this pyrite would look like actually, if you have a very nice picture photograph, to look like gold. It's called also false gold. Gold-like appearance, glittering yellowish color it will appear. You can see there's a very good cube shape, and there are more than 1 2 crystals that's stuck together. It's all it's a type of crystals are twin crystals. So you can see that type of specific shape, nice sharp edges, facets. These are some characteristic features of single crystal materials. In fact, we'll see silicon also as we progress in this course. it will have very nice, interesting face and structures. Okay, do you see slide number 5?
Yes, sir.
Okay, so this is about crystal lattices. Uh, for understanding, so you remember even in the um, waves and oscillation, we model, physics people model things. Okay, we observe the natural things that's going on in the world, and we model. We use equation and some picturizing, and then writing some equation and understand, and deeper, and then maybe formulate some equation how to utilize this effect, this phenomenon for real life applications, or some of our own use, or how we can control like this. Okay, likewise, to develop further understanding and maybe developing certain applications, knowledge, and control over the solid state materials, especially crystalline materials, people developed certain physics idea. So that involves crystal lattices and crystal structures. Okay, if you arrange points, just points, dots, okay, in space, maybe you consider one-dimensional space or two-dimensional space, it's a floor, okay, or three-dimensional. If you imagine, you arrange points periodically, means the distance between any 2 points is same in one particular direction, and the distance between any 2 points in another particular direction may be different from the other direction, but it should be same in that particular direction. Similarly, in the other direction, third direction also, or sometimes in all the 3 directions, the distance between any 2 neighborhood points will be same. Like that, you arrange points. So that is called lattice. The arrangement of points in space is called lattices. Now, the crystal structure of material is modeled with respect to these lattice points. You place the atoms or molecules. Okay. For example, with respect to one lattice point, you put a H2O molecule, H2O, one molecule. There is 2 hydrogen atom, 1 oxygen atom. So together it forms a hydrogen oxide. Okay, the H2O molecule, water molecule. You place one H2O molecule with respect to each lattice point. Okay, you may some cases need to place the molecule right on top of the at the center of the lattice point. Sometimes you have to place the molecule or atoms with respect to the lattice point slightly shifted to the right side or left side, or at some random direction, different particular angle like that. But it should be maintained for all the lattice points. So that constitutes the crystal structure. The lattice with which added basis set or motifs, that means the molecules or ions or atoms, that forms the crystal structure. Okay, crystal structure means the mathematical model or physical model is crystal structure is equal to lattice plus basis. The base lattice is nothing but arrangement of points periodically in space, and the base is nothing but atoms or molecules or ions which makes the crystal. You can think of sodium chloride crystal, NaCl crystal. Okay, which has Na plus and Cl minus, or sodium and chlorine. So with respect to each lattice point, you have to place a sodium chloride molecule. Okay. Now, as you can see here in the bigger picture in the bottom, this is a 3-dimensional lattice. You can see that there is a periodic arrangement of points in 3 dimension along the x direction, y direction, as well as z direction. So now I define the distance between 2 points along the x direction as vector A. Okay, vector A defines the direction, and the magnitude of it defines the distance between 2 points along the x direction. And similarly, along y direction, the distance between 2 points defined by vector B. And vector C defines the distance between the 2 points along the direction Z. Okay. Now I can also define the angle between them. For example, the angle between vector B and C as alpha, the angle between C and A as beta, and the angle A and B as gamma. Okay. We can say opposite to the vector A, you will have alpha. Opposite to vector B, you will have the angle beta. Opposite to C, you will have the angle gamma. This is a standard convention used internationally by whole scientific community physics people. So you have to follow the same. You must not change this. You should not randomly draw yourself as I will draw angle alpha as angle between A and B. That's wrong. That's not accepted. Okay, you have to maintain the standard notation. So these parameters A, B, C vectors and alpha, beta, gamma are called the lattice parameters. Okay, are lattice constants. So these lattice parameters, lattice constants, are very important in solid state physics. So depending on the lattice constant and lattice parameters, a material can have different properties associated with that. For example, if you consider carbon, carbon can exist multiple form, means multiple crystal structure. The charcoal, graphite is a hexagonal structure, and carbon can be in diamond structure. Okay, diamond is nothing but carbon atom. Okay, you remember charcoal, black stuff. Graphite, the pencil that we use writing on paper, graphitic pencil, black color. Okay, not transparent, it's black. But diamond, perhaps you have with you in your home. Maybe your sister or mom has it, or you might have noticed in movies and all, right? A lot of movies use diamond as a theme about smuggling or